Hello everybody, here I am today with a new video based on a static electric field. I'm going to explain what I have learned and what I found by myself studying several books. What is exactly static electric field according to my view? I'm not going to create any stuff here, but I'm explaining it according to my own view. Okay, see here. Static electric field means electric field is in rest here. First we start the four Maxwell equations. These are the four Maxwell equations. The first equation, second equation, third equation, fourth equation. And this is the expansion of fourth equation. First equation tells us that electric field, divergence of electric field is equals to rho by epsilon naught. Here rho is the charge density. The static charge density is rho. Means total charge by total volume of the setup. This is curl of electric field is equals to negative of the changing magnetic field. Divergence of magnetic field is equals to 0. Curl of B is equals to 1 by c square dE by dt. Actually the change in electric field here and change, this is not change, this is a j by c square epsilon. This is j is the current density here. And by writing it in more appropriate form, we can get it mu naught epsilon naught change in electric field here plus mu naught j. J is the current density here. Rho is the charge density, total charge by total volume. J is the current density. Current flown through a conductor divided by its cross-sectional area, that is say here. These are four important Maxwell's equations that is very, very important in electromagnetism. Now for static case, we'll have to bring whole setup stand still at a point. No movement, no changes with respect to time. So the terms containing differential with respect to time should be neglected. And then we get the time independent form of Maxwell's equation. That is this should be neglected. So we take 0 here. This is already 0. And here this is the time rate of change of electric field with respect to time. So this should be taken to be 0. And my fourth equation, the time independent form of Maxwell's fourth equation is equals to this. This is the time independent form, the simplest form of Maxwell's equation. Actually the Maxwell equations are quite tough to analyze in all the circumstances, but here in time independent form we have to start simply Maxwell equation in time independent form. Means the setup, neither electric field, neither magnetic field is changing with respect to time. And I'm going to analyze this. Actually, this time independent equation gives us a static case. Electric field is static, neither changing with time. And magnetic field is also static, neither changing with time. Okay? Pause it now. See, from the time independent form of Maxwell's equation, we have two sets of equations. This set contains two equations. This set also contains two equations. Here, these two equations have electric field, and this electric field is time independent, means it's not changing with time. Here, there are two sets of equations. Each equation contains a magnetic field, and both the magnetic fields are time independent, they are not changing with time. So once electric field is not changing with time, we call this electric field our static electric field, and so they gives us equation of electrostatic, means where electric field is static, is in rest, and we have to study that phenomenon. Here magnetic field is in rest, not changing with time, and it is magnetostatics. Pause it now. See, as we know, there are two charges Q1 and Q2 here. They are separated at a distance r. They have a force, either traction, either repulsion, based over the nature of the charges Q1 and Q2. This is F21, the force exerted over second charge by the first charge. This Q1, Q2 by r squared. I can write it like this. So the charge is here, and this is the entire effect produced by Q1 here. And what is this? In electrostatic term, this is called electric field at point 2 by charge 1. Means to produce force over Q2 by Q1, we need an electric field by 1 at 2. This is the value of static electric field as point at the charge 2 by charge 1. And from here we should know about electric field by Q1 at the point of Q2. So to process the force, to exert the force over Q2 by Q1, Q1 needs something that is called static electric field. Similarly, if I inverse the equation, Q2 is also applying on Q1 the same amount of force, and in the case of Q2, Q2 needs a static electric field to produce force over Q1. So, static electric field at Q2 is dependent on charge Q1 only. See, I have explained for one charge to one charge system. Now I'm explaining what is a static electric field for multiple charge system. See, there are several charges Q1, Q2, Q3 and Q4. Q2 is here, Q1 is here, Q3 is here, Q4 is here. Means I'll have to find a static electric field at Q2 by all these charges. Distance between Q1 and Q2 is R21. Distance between Q3 and Q2 is R23. The name reveals that the distance of second charge from third one. And this R24, distance between Q4 and Q2. See here, as we know, two charges can apply electrostatic force over each other. So the force F21, force over second charge by first charge is this, force over second charge by third charge is this, and force over second charge by fourth charge is this. And as we know, forces are vectors, so we'll have to add total force at Q2, total repulsive force at Q2 by vector addition. And I have done here the same thing. The values Q1, Q2 by R21 square, Q3, Q2 by R23 square, Q4, Q2 by R24 square, and 1 by 4 pi epsilon naught is inevitable with electric field. Electrostatic force. Here, take common Q2, that is Q1 by this, Q3 by this term, Q4 by this term. So what I get here, if I'm going to compare it with my one charge to one charge system, this is Q2, and this whole thing is giving us an static electric field at Q2, which gives a roadmap to these forces to make a relation with Q2. Means Q2 is experiencing force by all these charges due to their fields at Q2, due to their static electric field at Q2. And finally, I have written it here in terms, this F21 plus F23 plus F24 is equals to Q2, and this term goes for electric field at second charge by charge 1 plus electric field at second charge by charge 3, electric field at second charge by charge 4. And this is the total force at Q2, and this is the total electric field by the charges Q1, Q3 and Q4 at Q2. And finally I can write the result of this analysis at Q2. Total force, total electrostatic force is equals to this, Q2 into total resultant electrostatic field at that point. Means, from this conclusion, I can say that electrostatic field is just a medium to run the force over it. And force, electrostatic force, in my previous video, in my second video, analysis of electrostatic force, I discussed what is actually electrostatic force according to my view. The charges wants to make a relation among them, and they make their relation on the basis of their electrostatic force. Force is just influencing each other to make a relation, and that relation, that force needs a medium. That medium is static electric field here, positive. See, at M, if I have a mass M here, then the total resultant force over mass is visible or is identified through the resultant acceleration. Suppose the mass is here and if it has acceleration AR here, resultant total acceleration over mass m is here. It means that the net resultant force is in this direction by Newton's laws of motion. The same thing, by comparing these two equations, Fr is equals to QER and Fr is equals to MAR. Here in electrostatic, a charge is under the influence of electrostatic force, then it has something, a physical quantity arrives here, that is a static electric field. See here, whenever we have charges, but it is quite different than the same. We can compare the analysis, but we have to be careful to the signs because why charges have different signs and masses haven't. It is positive Q, it is negative Q. If a positive Q is kept in a static electric field, then it experiences force along the direction of electric field, means it shifts towards here. That's why the the electrostatic force over plus Q is in this direction. If a charge is minus Q and it is kept in a static electric field here in this direction, then it experiences electrostatic force opposite to the direction of electric field, and that's why it is minus Q, it is kept in this electric field which is in this direction, so resultant force is in this direction. That's the difference. But one thing is clear here, as to determine resultant net force over mass, we need acceleration, or we need to identify acceleration. Similarly, to identify electrostatic force over positive charge, we need an electric field here, and to identify electrostatic force on minus Q charge, we need an electric field which is static in nature at that point. Forces are opposite to electric field when charge is negative. Electrostatic force is in the direction or along the direction of a static electric field when the charges are positive. Go. See, as I have discussed, force needs medium to apply. I told you that electrostatic force is the relation between the two charges. They want some relation, and that relation is electrostatic force. And the relation, the exchange of relation, needs some medium. And that medium is electrostatic field at that point charge. See, there are two persons, A and B, or some name A and B. A wants to exert force on B, means wants to put an effect over B, and this time A is trying a punch here. So the relation, the effect of A on B with the virtue of force is through this punch, means the medium is punch here, that is the muscular force.
Right A and B
The
there.
second case, wait, yeah, I need to write here, where's the marker? Yes. I need to write here, here's A, here's B, here A and B. Second case, when they are quite separated, the separation between them is quite long in this case. A wants to make a relation, wants to give some effect to B. This time, he has to again use the force, but the distance is quite long, punch is not possible to reach there, so it's not muscular force. But in the exchange of muscular force with the mechanical force of a stick, and A uses a stick to hit B. So, to apply force by A on B, in each case, we need a medium. I don't need medium. The force needs a medium, and force is the relation, the effect. Similarly, the charge also needs a medium to exchange their relation, to bring some effect to each other. Q wants to put some effect to a minus Q, and minus Q wants to put some effect to a plus Q, and that's why they exert repulsive force. So as this force requires some medium, punch or a stick in this case, here this force requires a medium to travel over there. That medium is electrostatic electric field. For Q to put its force here, this force travels over electrostatic field, and the effect of minus Q, relation of minus Q plus Q, also needs the force that is towards plus Q, and it also travels on the same electrostatic field. The mechanical analog of this electrostatic electric field here, or static electric field here. Suppose this is a two-way road, so the road is quite broad. This road represents electric field. There are two cars. This is car 1 and this is car 2. The car 1 is loaded with positive charge, car 2 is loaded with negative charge. Here I'll have to neglect the friction or all mechanical forces, what we have studied in mechanics, friction, gravity or something. We just have to think the force in terms of repulsive or attractive electrostatic force. This car is overloaded by plus Q, this car is overloaded by minus Q, and they are on this road. Now, what they do? They will attract each other. Means the effect of plus Q or minus Q, the relation plus Q is going to be with minus Q is the attractive force, that Fe. And similarly, that minus Q or this plus Q is also making a relation that is Fe. Both the forces are equal. It applies the same force to this and it applies same force to this. So the net force within the closed system, according to Newton's law, within this closed system, the net force is 0. But it also experiences some force, it also experiences some force, and they are acting towards each other. This force is the relation, and this relation needs a medium to travel on. This force needs a medium to travel on, and that medium is the electric field between these two charges. So for the effect of plus Q minus Q, there's a medium runs from plus Q to minus Q, and through that medium, the force exerted by plus Q or minus Q travels on. For the effect of minus Q or plus Q, there's a medium goes from minus Q to plus Q, and through that medium, the force of minus Q or plus Q travels. Understood? This is the concept of static electric field. It's just the medium in one case. Actually, we cannot say what's happening completely and with a lot of precision, but this is quite probable and very, very close analysis of a static electric field. And we studied deeply about these things in our wave electric field when we read the electric field, wave nature of electric field. And for the precise analysis, we study quantum electrodynamics, but this is the classical electrodynamics, not electrodynamics, but electrostatic. This is this. See, what happens if the force will be repulsive? Pause it now. See, what do we notice here? Whenever the charges are opposite in nature, they attract each other. And these two cars representing the two charges, whenever there is minus here and here's plus, they rush towards each other. On a road, that road is the electric field. A mechanical analogous of electrostatic concept. But when the charges are positive, both are positive or both are negative, then they have repulsive electrostatic force. And the charges experience force over there away from each other. And that's the case when both the cars are loaded by plus Q and plus Q. They have repulsion and they will go away from each other on this track. This road is electric field. And now think, here within the system, the total force is 0. Remember all that, the total force is 0 within the system, two-charge system. So these forces are internal forces and they cancel each other. So the center of mass of the charge, if there were mass, if there are mass of the charges, then the center of mass is constant because there's no external force, even in case of attraction and in case of repulsion, positive. We know that the charges are opposite in nature, they exert electrostatic force that is attractive in nature, and when they are same in nature, they exert repulsive force in nature. That's the concept here. Over an electric field, there are two cars carrying plus Q, minus Q, they rush towards each other. Over an electric field road, there are two cars carrying plus Q, they rush away from each other. Suppose there's a car which carries plus Q and there are four cars at equal distance in all the four directions. They are carrying minus Q, minus Q, minus Q each, and the distance is same. What happened? These two cars have attraction and they rest towards each other. But here it's also the attraction here, and these cars attract each other. Then what happened? This car is not going anywhere. These two cars are coming here. Similarly, this car and this car are attracting each other, and hence here this car and this car are also attracting. So this car is not going anywhere, and all the four cars are coming towards plus Q. Means this car is attracting all these cars. Means car 0 is attracting car 1, car 2, and car 3, and car 4. And if I have innumerable number of cars carrying opposite charge equal in magnitude at a distance equal from plus Q, then what we can see, all the cars at a distance are carrying minus Q, rushing towards car 0. And what is the road map? The road map will be like this. And this road map represents that there are innumerable roads possible from plus Q to make a relation, to put an effect over the charges which are opposite in nature or supportive in nature in the premises. So we can say the electric field over a point charge is spreads in a 3D space. We have electric field over a point charge in a 3D space. And that's my static electric field. Now in next video I can show static electric potential, and then I give you a broad view of electric field with respect to electric potential, keeping these things alive but in a new way. So thanks for watching. If you have any kinds of doubts and if you find any error in my explanation, I'm a student also, so you can send me over my Instagram, my Facebook, and my YouTube channel. My YouTube channel is Physics Defines the World.
Right in there.
Yes, correct now.